Good, then let's continue. So the first thing now I want to discuss a little bit is how to summarize the posterior distribution, because of course in practice it's sometimes useful to have, instead of just giving someone a posterior distribution over a parameter, to give them or yourself a specific number. So instead of saying the parameter is now normally distributed with a expectation parameter of 2 and a variance of sigma square. Of course, you know that these values already tell you quite a lot, but it might also be useful to just say, okay, from a Bayesian perspective, the parameter is something like 2, or it's in a certain interval. And this is then the topic of this inference summaries business. So first thing, Bayesian point estimation, and the next and a little bit shorter thing then Bayesian interval estimation. So from the perspective of the Bayesian paradigm, of course, the central entity that you're dealing with is the posterior distribution over the parameter. So describing your uncertainty over the parameter in light of the information that is provided by the data. As I said, point estimates can be helpful. In the Bayesian scenario, when talking about point estimation, it's usually framed as a decision theoretic problem. For some reason, this also survives in machine learning. So there you sometimes have these kind of decision theory sessions in machine learning. And the most important thing to then establish Bayesian point estimators is to introduce something like a utility or loss function, which is also quite natural and which in the frequentist scenario doesn't really exist. So what do I mean? So first the question is, what is a loss function and what is a Bayes estimator? So we're starting now always from a probabilistic model. So this is similar to the assumptions that we made earlier all the time, that we have a parametric statistical model with independent identically distributed data points. Now we always start with this joint distribution of a parameter and data points, a probabilistic model. And now we assume that we also have a point estimate for the true but unknown value of the parameter of the probabilistic model. So again, this is our uncertainty in the world. There is one true but unknown parameter, and we use our estimate here for this true but unknown parameter in the world. So we somehow need to, from our, for example, from the posterior distribution, summarize the distribution into a single number. For example, the expected value of the posterior distribution, which we will see in a second. Then what we can define is a loss function, namely a function from the square of parameter space to the real numbers, which we assign to each value of our estimator and each value of the true but unknown parameter value. And with this loss function, we want to encode our undesirability of choosing a specific point estimate if the true but unknown parameter value is theta. Yeah? And I will give specific examples in a second so it gets clear what this is about. One can also define things not in this kind of negative setting of loss, but in the positive setting of utility. So you can also define utility functions, and utility and loss functions are can be shown to be related just by changing the sign of the utility. But then if you do this probably according to the Reifer-Schleifer statistical decision theory framework, there is an additive constant which also differentiates utility and loss functions. So I did everything here in loss functions, so we don't worry about the relation between utility and loss. We just start with loss. And the question then is, and the basic objective function that we're interested in is, in Bayesian point estimation the expected posterior loss. So if I have a certain probability distribution, posterior probability distribution over the parameter, and I integrate and weigh my loss for a specific parameter, estimate over all possible values that the parameter can take on by this posterior distribution. So I average essentially the loss function with respect to my posterior distribution. And then I get a function that is only a function of the estimate, and this is called the posterior loss. Yeah. So essentially to compute the posterior loss, you need to specify a loss function. So how much do you punish deviations essentially from the true but unknown parameter in terms of your estimator, and then think of course you want to punish more if you assign a lot of probability density to a given value. It will get a lot clearer once I give you the example in a second. The important thing is that if you have the posterior loss, if you computed the posterior loss, then you can, of course, have the aim of minimizing that. Of course, why should you maximize your loss? So you want to minimize your loss. And you can find a point estimate, because this loss function depends on these values, that minimizes the expected posterior loss. This estimator, so in a way, if you want, analogous but very different from the maximum likelihood estimator, which maximizes the log likelihood function, and this point estimator minimizes the expected posterior loss function. And this point estimator is called Bayes estimator. Yeah, so if you ever read something about the Bayes estimator, a Bayes estimator is the minimizing value for the posterior loss function, which is your loss function that you need to define integrated under the posterior distribution. So, of course, then the exact form and the exact form and type of a Bayes estimator depends on your loss function, clearly. Let's look at examples for different loss functions. So the first example here is a quadratic loss function. That's a very common thing, of course, to do. So you basically, what this loss function encodes is that you incur loss if your point estimate deviates from the true but unknown parameter, and if you are further away from that, you punish that more because you have the square relationship. Yeah. So if you are estimating the true but unknown parameter value with completely correctly, then you have zero loss. But the more you deviate from the true but unknown parameter value, you punish your loss more and more. Yeah. So that would be a quadratic loss function. You can have other loss functions. One of them we will see on the next slide. Another one we will see in the Übung. Now, the question is then, what's the Bayes estimator under a quadratic loss function? And one can show, and this is on the next slide, one can show that the Bayes estimator under a quadratic loss function is the posterior expected value. Yeah? So you have a posterior distribution, then of course you can compute the expected value of the parameter under the posterior distribution. That's nice. So I already said, like for a univariate Gaussian, maybe you have a univariate Gaussian as a posterior that has a certain expectation parameter. Yes, you can give this as a point estimate. The question is, what does it mean, and how far is it a good estimate? Well, it's the optimal estimate under a squared or a quadratic loss function. So the Bayes estimator under a quadratic loss function is the posterior expected value. And this estimator is also known as the minimum mean squared error estimator, because you might remember that mean squared error is exactly the expectation of the squared deviation here. And because this is minimized here, it's called minimum mean squared error. So why is that so? So that's just a little proof. So the first question, of course, so what you need to do then, if you want to find the specific base estimator under specific loss function, you need to minimize the expected posterior loss. And for that, it helps to first write down the expected posterior loss. So this, of course, here takes this form. You just, for the loss function, you plug in this squared deviation. And then the way this proof works is that you now want to minimize the expected posterior loss. So you do the typical thing, you compute the derivative. I mean, we have a square function, so you know there's a single minimum. You compute the derivative and you set to 0. So, and you assume that you can do things like changing the order of integration and differentiation. So computing the derivative with respect to, because you want to minimize with respect to your estimator, you take the derivative with respect to theta hat. Of course, then the only thing that depends on theta hat is this square expression here. You get rid of the square, and nothing else happens. And then you set to 0, and this, so 2 cannot be 0, so this needs to be 0. And then the integral is of course not depending on the hat, so you can get the theta hat out, and then you already have that the minimum of the posterior of the expected posterior loss function under a squared error loss function or quadratic loss function is the posterior expected value. Yeah. So the point here is you have a posterior distribution, and you now want to give, instead of just saying this is my posterior distribution over the parameter, I want to give someone a single number. Then of course I can take the expected value of my posterior distribution, but the question is, why would I choose the expected value and not, for example, the median or the mode? And the argument is, well, if you punish deviations in a squared from the true but unknown value in the squared sense, then using the expected value is a good thing to do. So this is also typical base that you maybe even more so than, I mean, when we discussed maximum likelihood, we first just made it very intuitive. Yeah, you want to maximize the likelihood, and also in the whole in the development of statistics, of course, the asymptotic optimality of maximum likelihood estimators was found much later. These things are much closer together. So in Bayesian inference, there's a lot more thinking about why are we doing this and under which conditions is this a good thing. And this is the first thing where you see this. Of course, it depends on the loss functions. Any questions so far about this? Because now we look at a different loss function. Down a question right now. This would be the 0,1 loss function, which penalizes a deviation from the true but unknown value with a 1. So that's the biggest loss you can incur here. And so if you don't estimate with your point estimate estimated true but unknown value correctly, you have a loss of 1. Otherwise, you have a loss of 0. And this is encoded here. So this is the indicator function. So if theta hat equals theta, then you have 1, and hence you need 1 minus this to get 0 loss if they are the same, because you don't want to have any loss if you're doing it correctly, and 1 if you're not doing it correctly. Now, under the 0,1 loss function, the base estimator, so the estimator that minimizes your posterior loss, is the posterior mode of the parameter, meaning what is also called the maximum a posteriori or MAP estimator. Of course, for a Gaussian posterior, this is somewhat lame, because for a Gaussian, the maximum a posteriori, there's a typo, and the minimum MSE, minimum mean square estimator, are the same thing, because the mode and the expectation of a Gaussian are the same, but this is, of course, not always the case for other distributions. So again, under 0,1 loss function, the base estimator is the posterior mode. So the value that minimizes the posterior loss is the value that maximizes the posterior distribution. And this is also referred to as MAP. Yeah. I think often in machine learning books, at least, when posterior distributions are introduced, then it's often said, yeah, then you can use a MAP estimator. It's maybe set more than you can use the expected value of the posterior distribution. So why is this? So again, you can show that by putting in your loss function into the expression for the expected posterior loss, and then you can put it in here, divide it into two integrals, and one of them just integrates then over the posterior distribution with respect to 1, so you get 1 minus, and here you integrate over theta, so this only is 0 all the time, but if theta hat equals theta, so you get out p theta at the location p theta hat, so you get this expected posterior loss function, and then if you want to minimize this, you 1 minus p theta hat given x1 to n. This is of course the same as maximizing this thing that you subtract from 1. And then you've already shown that the map is the base estimator under a 0,1 loss function. The last typical example that always happens is that you always see is that you use absolute error. So instead of using a squared deviation, you use the absolute value of theta minus theta hat, and it turns out that the median is the base estimator. In this case, this is something for the Übung. We'll do that in the Übung. Yeah. So now we've seen base estimators. So expected posterior. So we've seen base estimators, we've seen the expected value of the posterior estimation as the minimum mean squared estimator, we've seen the maximum posterior estimate, so the mode of the posterior distribution as the base estimator under 1,0 loss, and I told you that the median is the base estimator under the absolute error loss function. But already note that we have now 3 base estimators, so 3 point estimates, and in frequentist statistics we mainly dealt only with one, namely the maximum likelihood estimator, although there are also more. We talked about the methods of moments for estimation, so of course also in frequentist statistics you not only for point estimates deal with the maximum likelihood estimator, but mostly you do. Good, so that was a little bit on inference summaries in terms of point estimation. Next thing, questions about this? Yep.
I'm not sure if I got it completely. So with this, you're in the loss function, the theta, the unknown parameter, you have to specify. How do you calculate if you don't know theta? So theta.
Which theta? Head theta? Or?
No, not theta. Theta head is the estimate who. Yeah. Yeah.
Well, you don't calculate that really, because it's always entering the. So 2 things. So first you need to, in terms of the pure loss function, you need to come up with some penalization scheme. So you need to say something, okay, if theta hat and theta have the same value, then I've done okay, because my point estimate is the same as the true but unknown value. If they are not the same, I have to specify how much loss I want to associate with that. And this is like this 1,0 loss, or the squared error loss, or the absolute error loss. And then what you have from Bayesian inference is always the posterior distribution. Yeah, so you can always have the posterior distribution, and then what you need to do is you need to integrate over this all the possible true but unknown values which you described with your uncertainty. So you don't ever have to really calculate anything with this theta, because you integrate over it. Yeah. No. Any other questions? Good. So a little bit shorter, the summary in terms of Bayesian intervals. Again, starting with that the central entity is the posterior distribution. again, you can argue that just dealing with the posterior distribution is sometimes too much, and you want to now know something about an interval. And then, of course, it's very natural if you have a posterior distribution over a parameter to say, okay, in this interval in parameter space, there is that and that much probability, or better to say, the probability that the parameter lies, for example, between 0 and 2 is 95%. And of course, this is then contrasting with confidence intervals, as we discussed in pro-frequentist statistics. And to make the distinction clear, the Bayesian interval estimates are called credible intervals, but I think it's also important that you shouldn't think about whether credibility or confidence are different things, because these are just words, these are just pointers to these things. The difference in confidence intervals and credible intervals is in how they are created. Yeah, so it's not that a credible interval is per se better than a confidence interval because it's more credible. And the other one is just about your confidence. Is completely irrelevant. They could be named the other way around, or they could just be called Bayesian interval. I think the best thing would be if one just called them frequentist interval estimates and Bayesian interval estimates. Then it's clear and one doesn't get into discussions about my confidence and isn't my subjective uncertainty also my confidence and stuff. It doesn't make sense. It's just the name, and it refers to the Bayesian interval estimate. And one can argue that credible intervals are more intuitive than confidence intervals because they, remember when we discussed confidence intervals, we discussed their interpretation in that they cover the true but unknown value in that many cases if you sample again and again. Here, of course, it's more straightforward because you have a distribution over the parameter, and you can, to each interval of the parameter, assign a certain probability. So based on the data, the probability that the parameter lies between 2 and 4 is 60% or something like this. The notion of a credible interval, like for a confidence interval, can be generalized to a non-scalar parameter by calling these things regions, because then they are always intervals only if you have a real value parameter. That's, of course, where you have intervals really, but if you go to multidimensional parameter spaces, of course, intervals are not really defined anymore, and you have to come up with other ways to define regions. So what is then a delta credible region or delta credible interval? Well, you have a probabilistic model with parameter space theta, and you have the posterior distribution, and then any region such that the integral over this region of the posterior distribution equals delta. So for example, say delta 0.95. So any region that if you integrate the posterior distribution over that region, you get 0.95 is a posterior delta credible region. If it's an interval, then it's a delta credible interval. The thing is, this is, of course, not uniquely defined. So maybe I should draw that. So if you, of course, what we're talking about here is something like this. And maybe you have some posterior distribution like this. And now you're saying you want an interval where 95% of the probability mass is located. Of course, you can, so this is supposed to be non-symmetric here. Actually, also has somewhat of a tilted x-axis, but ignore that. Of course, you can put 95% of the probability mass here, or so that could be something, or you can put 95% of the probability mass here and just go further out here, something like this. Yeah. So just to say 95% probability interval doesn't uniquely specify which interval it now is, and then this is actually also true for confidence intervals. In confidence intervals, we mainly ignored that fact because we dealt with symmetric distributions, and we always assumed that symmetric confidence intervals are good. But of course, in confidence intervals, you have the same problem. If you have other distribution of the statistics which are not necessarily symmetric, then you also, for example, if you have a chi-square distribution based on for a variance parameter, then you also don't really know where to put the interval boundaries to achieve this coverage probability, as you are not really sure here how to achieve that there are 95% of the probability mass. But you can, of course, give yourself different rules, and this is then what in credible intervals is discussed a little bit more at length, but I will not go into that. So you can, of course, try to find the minimum size delta credible interval, so basically to play around with the interval boundaries until it's as small as possible over the entire space, but has 95% of the probability mass. You can do symmetric credible intervals about the posterior expectation, so that you have how much? 42.5 on each side of the posterior expectation. So even if it's if you have a non-symmetric distribution, so if you have something like this, but always can only draw symmetric things. Well, it's somewhat non-symmetric here. So if you have somehow the posterior expectation somewhere, then you say, okay, I want half of this thing here and half of the thing here. Or you can do equal upper and lower tail probability credible intervals, so that you cut off if it's non-symmetric. I can only draw symmetric distributions. What's going on? How do I draw a non-symmetric distribution? Something like this, that you put in half here and half there. Oops. Very nice. So these are things in Bayesian credible interval intervention one can think of. That's as much as I want to say about Bayesian credible intervals. So the main thing is you have the posterior distribution, and then you can give intervals where most of the probability mass of your parameter is located. But you have to think a little bit how you do that, which also will then depend on the form of your posterior distribution. Good. So this was essentially most of the theory that I wanted to give about Bayes. So the Bayesian paradigm, joint distributions, and all its marginal and conditional distributions, and then you can summarize the posterior distribution. In the next, so in the remainder, then there will be some examples. And in the other lectures, we will look at different ways of actually doing Bayesian inference when we talk about the numerical approaches and talk about variational inference. And we will see an application of this in Bayesian filtering. But in terms of the theory, this was basically it. Of course, one can write thick books about Bayesian theory. So Bernardo has written a lot on Bayesian theory. In machine learning and data science and so on, Bayes inference then happens more on the level of these examples that we will also now look at. So after the theory, now let's look at examples. And the first thing that is in some way now, if you think about frequentist statistics, analogous to analytical maximum likelihood estimation, because you just think and write down and prove things, and then you have some estimators, or in this case posterior distributions, from which you can derive Bayesian estimators, as we've just seen, or intervals. But you just think, you don't have to turn on a computer. The other thing is that you do numerical maximum likelihood estimation, where you use some iterative algorithm to find maximum likelihood. This is more what we will do in numerical methods for Bayesian inference and variational inference. So conjugate inference you can consider or conceive as the analogous approach to analytical maximum likelihood estimation in simple models where this is possible. So what is meant by conjugate inference? Conjugate inference basically rests on, again, the assumption of a probabilistic model and the conditional independence of the data points. and then starts with a family of distributions phi over theta, and phi is called, so this is a definition from de Groot and Scherwisch, phi is called a conjugate family of distribution with respect to the data likelihood if the posterior distribution is an element of small phi, that's wrong here, is an element of phi irrespective of the prior distribution, which is also in phi, and the observations. What this wants to say is, if your prior is, for example, a beta distribution, you sample some data and you inform your prior distribution based on the data, and your posterior distribution is again a beta distribution but with different parameters, then it's a conjugate case. So in the conjugate case, the probability distribution type of the prior and the posterior is always the same. What is of course not the same is the specific form or the specific instance of this distribution, because you update your prior distribution to a posterior distribution. But this is this idea of conjugacy, so that you have a prior, you have, of course, this needs the right likelihood, so this doesn't happen with any likelihood, so this is why this conjugacy is with respect to some likelihood. But then your posterior distribution is again of the same type as your prior distribution. And this is also referred to as closed undersampling. Of course, the sampling is here the sampling of the data, not sampling of a parameter. Then usually what happens, as we will see in the examples, is that the prior distribution has some parameters and the posterior distribution has some updated parameters, and these parameters, because they are not the parameters that you're actually interested in, these are the thetas, and these parameters of your prior and posterior distributions are called hyperparameters. But yeah, I don't use the term hyperparameter that often because it sounds a little bit pretentious, I think. So that's kind of the definition. There is actually a whole class of probability distributions, namely the exponential family, where you can do conjugate inference. Does anyone know the exponential family? Has anyone studied the exponential family? That's a family of probability distributions where most of the distributions that you come across, like Gaussians, betas, don't want to go wrong. I think one of the things that always comes across is not in there. But T distributions, all these things, they are all in the exponential family. So one could also, if one introduces conjugate inference, just do this now for the exponential family. However, I opted to do this for a very specific, or at least two specific models, to show you closer what's actually happening, and not because then if you go into the exponential family, you need the notions of statistics, and you have all these, you have these distributions that you've never seen before, or let's say you have this exponential family which looks different, then you need to show that all that distributions that you know are special cases of that, and so on. So you need some more theory. But the nice thing about doing exponential family is that conjugacy doesn't look that random, because if you do what we are doing now, so we look at specific examples, the question is a little bit, why does it work here and why does it maybe not work in some other case? And is there a general way I can derive posterior distributions analytically? And yes, there is, but you need the exponential family business for that. Here we look at specific examples and derive posterior distributions using our intuition, which of course is not helpful if you want to do that again in some other settings. So a lot of talk. Now let's look at a first example of Bayesian inference in a real model, because so far we've, or in an exemplary model, because so far we've just talked about general, the probabilistic models, and you can do these things. Now let's make this more concrete. Namely, we talk about the better binomial model, where you talk about data that takes on the values 1 and 0. So your data takes on, well, that's not quite correct actually. Your data takes on, your data sequences essentially take on, it's horrible with the binomial model. You always think it's about ones and zeros. It's actually about the number of ones in a data sequence. Yeah? So the way you can think about it is you look at the distribution of the number of ones in sequences of ones and zeros. You can view this as the extension of Bernoulli samples to independent multiple times, but you need to be a little bit careful because it's really as I just was confused, the outcome variable are values between 0 and the number of data points. So for example, if you have 10 data points, and for each of these data points, the probability to assume the value 1 is theta, and then you ask what is the probability of 9 ones in there. And then, for example, you have observed 5 ones in there, and you now want to estimate the parameter. So this is the case of the better binomial model. So the outcome variable, the number of ones in a sequence of n's, zeros, or ones, and a natural prior distribution, because this parameter for binomial distribution is obviously the expected value for each of these single ones is the theta. And because this is a probability, a natural prior distribution here is the beta distribution. So before I show you this, just want to remind you of binomial and beta random variables. So maybe I should have done that before I showed you that. The binomial random variable is the random variable with outcome set 0 to n, so 0, 1, to n, and this probability mass function. So it assigns probability to these values from 0 to n, and you compute it like this. We've seen that previously, and the important, or one important thing is that the binomial for the case of a single data point is the same as the Bernoulli. And if you have independent sampling for multiple Bernoullis and you sum them together, then you get the binomial. We also seen that in the Übung before. So there is a close relationship between Bernoulli and binomial, but one has to be a little bit careful there. Alternatively, what we could have done here is do Bernoulli, the better Bernoulli model. Why I didn't choose the better, or why I didn't choose the Bernoulli is because then you always have only one data point, and that's interesting when we do cognitive neuroscience. But in real life, you usually don't update your distributions only with one data point, but you acquire some data, and then you're in the case of the binomial model. The beta distribution is a continuous distribution over the interval 0, 1, and it has this probability density function. It is depending on two parameters, which are called alpha and beta. So these would be hyperparameters in our setting, and is because it's a distribution over the interval from 0 to 1. It's often used to model parameters that refer to probabilities, like the success probability in a binomial distribution or Bernoulli distribution. And then these beta distributions, depending on their parameters, look different. So for example, if the parameters alpha and beta are 1, then you have the uniform distribution over the interval 0 to 1, so this stops here. If you, for example, have many alphas, so if you have something like alpha equals 5 and beta equals 1, then you get a distribution that is constrained to the interval 0 and 1, so it's not a Gaussian or something, so it's a better distribution, but it assigns more probability mass to one side. So I think the alpha encodes in the direction of 1. If it's the other way around, so for example, if you have a very high beta value but very low alpha values, then you might get something like this, and it's always constrained to this. So it makes sense to encode uncertainty over a parameter that is modeling probability, it makes sense to encode this in a beta distribution. Now, because it's a conjugate distribution, and this is then how conjugate inference always works, is that you specify your prior distribution with alpha and beta, which, for example, with 1, 1 would encode a uniform distribution over the interval 0, 1. And then, based on the data, you can simply update your distribution by updating the parameters of the beta distribution. In this case, it would be alpha plus x, so the number of observations of ones that you observed, or the number 9, for example, if you have 10 observations, and the beta by plus n minus x. Based on this posterior distribution, you can evaluate the posterior expected value based on the properties of the beta distribution as this, and of the map estimator also based on this. The good thing is I'm running out of time, and this is good because then this means that we can discuss the proofs which are included here in the Übung, and that should be then fairly straightforward because it's all there. Another case for this form of conjugate inference is the Gaussian model, which models Bayesian inference for the expectation parameter of a Gaussian. So here, this Gaussian here would be a normal distribution over data points for one parameter with its associated variance, for which we already did things like maximum likelihood estimation. There's this I did not say. One can look into this and actually see, and this is something you can also see in the Gaussian scenario, that the posterior expected value in the beta scenario is a weighted average between the prior expected value and the maximum likelihood estimate. Yeah? So if you have, and this weighting is done according to the uncertainty that you have about each of them. I think we really should do that in the Übung in some depth, so that gets clearer. The thing with the Gaussian is the same thing. You have here your data distribution, here you have the prior. You can again get the parameters of the posterior distribution by essentially using some formulas that involve your observed data, so in this case the average of the data, and your prior parameters for the expected value of the or the expectation parameter of the posterior, and similar for the variance parameter. And again, this needs a little bit of a proof, but when you look at it, you can again show that the posterior expected value is proportional to a weighted average of the prior expectation and the data, and the data, and in this case the data summarized as maximum likelihood estimator. Yeah, so you get basically with the Bayesian inference in the conjugate setting, you go beyond maximum likelihood estimating by accounting for prior information that you might have. This was a little bit fast now. There are some shortcomings, especially, for example, to this Gaussian model that I've just shown you, because this is just Bayesian inference for the expectation parameter of a Gaussian. But of course, you already know how to do frequentist inference, not only for the expectation parameter, but also for the variance parameter of a Gaussian. If you want to do that in the Bayesian inference, you need to specify also a prior distribution over the variance parameter, and there you can do what is known as the Gaussian gamma Gaussian model, which then does Bayesian inference for the univariate Gaussian for both parameters in a conjugate setting, namely for the expectation and the variance parameter. And you can also, from better Bernoulli or better binomial, go to a generalization of that, where you not only have one-dimensional outcomes of ones and zeros, but multi-dimensional outcomes that would be the Dirichlet multinulli. Then you can do the whole thing multivariate in the Gaussian setting, and you can also do the Gaussian, multivariate Gaussian with a prior on the covariance matrix. This is the Gaussian-Wishart Gaussian model. And as I mentioned in the beginning, all of these examples are actually examples for conjugate inference in the exponential family. So I would suggest we will look into that really in the Übung, so that you get a good feeling again for what it means to do a Bayesian inference in the conjugate setting, so that we also discuss the better binomial there again and the Gaussian there again, I guess. Yeah, because the thing is, once you've done these examples and worked through them, then they are clear, and it's also it would be a little bit of it would be very boring if I now for the rest of the term go over these one example and another example and another example. That's something we can do in the Übung. Here we do more the grand ideas in the lecture. Yeah, good. Questions right now? No. Good. So next week we will then basically move on from Bayesian inference when the parameter is constant to when the parameter is shifting, so Bayesian filtering, and looking at examples of Bayesian inference in the conjugate setting where you can do things analytically will be happening in the Übung, as I said now 10 times. Good. Then let's meet again in a few minutes in the Übung. Bye.